How are we doing today? Hopefully y'all are doing well. So today we're going to be continuing our notes on chemical reactions in Unit 4. So for this, we are going to be focused on our acid-base reactions. Now, you do need to make sure you've got everything for your notes. So go ahead and grab that. So notes, paper, pen, all that kind of stuff. You will also probably want a periodic table as well. All right, so let's go ahead and dive on into these notes. So what are acid-base reactions? Well, they are a type of double replacement reaction. Now remember, with double replacement, what we've got is we've got two compounds, right? And in these compounds, we've got a cation and an anion in each one. Well, what happens with them? Well, those cations and anions, they swap places. So your cation from element A is bonded with your anion from element B and vice versa. So we're just going to kind of have them swap places, and then that would get a double replacement reaction. Now, for acid-base reactions, we're going to have two big things. We're going to have an acid, and we're going to have a base, right? So what are an acid and a base? Well, our current definition, our Bronsted-Lowry definition for acid-base reactions, is that an acid is going to be a proton donor. And so what that means is that the reactant that it is going to lose a proton. Okay, so it's going to donate it or give it away. Okay, in the base, it's going to be your proton acceptor. So it's going to be the reactant that is actually gaining a proton as a part of this reaction. Now, a part of this is we're going to have these things called conjugate acids and conjugate bases. Essentially, a conjugate base is what is left of the acid on the product side after it donates the proton. So what we're looking at is our acid, as it goes through this acid-base reaction. Acids, remember, they donate a proton, so it's giving away this proton. So its conjugate base is the result of, or is what it becomes after it donates that. Okay, the conjugate acid is the opposite. So the conjugate acid is the base after it has received its proton. Okay, so what we're going to do is we're actually going to identify, first off, what is a conjugate base and what is a conjugate acid. For a conjugate base, remember, if we've got our acid, the acid is going to be the proton donator. It's going to lose a proton. It's going to lose a hydrogen. And remember, the conjugate base is what's left over after that. So when we're thinking about conjugate base, it should always have one less hydrogen than the acid did, right? Because the acid was what was giving away a hydrogen. So looking at our conjugate base here, I've got HCl. So after that HCl gives away that hydrogen ion, we're going to get chlorine left over, right? But chlorine here is going to have a charge of -1. So my conjugate base of this hydrochloric acid would be Cl-, the chlorine ion. All right. Again, it's just showing that hydrogen being given away, and as a result, you're going to have a negative charge there. Okay. So here, looking at this HNO3, if we're going to give away a hydrogen, then we would be left with NO3-. Okay. So that's how we can identify what the conjugate bases are. So what I want y'all to do is go ahead and pause your video, work through the rest of these, and then we'll quickly go over them in just a second. All right, so pause your video. All right, so hopefully y'all paused your video, but let's go over these. So I have NH3, and its conjugate base would be NH2 with a negative charge. Why? Because we lost that hydrogen ion as a part of that acid-base reaction. Okay, so NH2 with a -1 charge. Then I've got HC2H3O2. So as a result of this, we're going to get C2H3O2 with a -1 charge. And then last, I've got CH3NH3 with a +1 charge. After it loses that hydrogen, it will turn into CH3NH2, and there will not be a charge there anymore because we got rid of some positives, so we would be left with something that's a little bit more negative there. So it would become a neutral atom there, okay? Or neutral molecule, sorry. All right, so now let's take a look at our base versus conjugate acid. So here I've got F-. So we know that the base is going to gain or receive a proton, Okay, so it's going to receive that hydrogen ion. So here I've got fluorine. It's going to receive a hydrogen. So we're going to get HF. Okay. Fluorine here had a negative charge. Hydrogen has a positive charge, so they're going to automatically cancel out. So let's look at our conjugate acid for NH3. So NH3, so we are going to gain a hydrogen. So we'll turn into NH4, but hydrogen has a positive charge, so it becomes NH4 with a positive 1 charge. Okay, pause your video, work these next two, and then we'll go over them real quick. Okay, so hopefully you paused your video, but let's go over these. So I have H2O. Again, the conjugate acid is going to be where it has actually already received that hydrogen ion. So I have H2O, and it will turn into H3O, but since hydrogen has positive charge, H3O with a plus. H2PO4 negative turns into H3PO4. All right, so that would be us identifying our conjugate acids and our conjugate bases. Now, what does all of that look like in terms of an overall reaction? Because AP Chemistry is not going to ask you what is the conjugate base, right? It's not going to say, if I have the acid, what is my conjugate base? All right, it's going to be a little bit more in depth. And so let's actually look at what they're looking for this. So I have CH3COOH, which was aqueous, plus NH3. And it's going to produce what? So CH3COOH is acetic acid. NH3, or ammonia, is a base. So here I've got my acid, here I've got my base. So what's going to happen is my hydrogen is going to be donated to my base. So this would be my acid, and this would be my base. So my hydrogen was donated to that. And as a result, instead of NH3, it would turn into NH4 with a positive 1 charge, plus, well, what's left over? So I have CH3COO, and then it's going to have a negative charge because it lost that hydrogen. All right, so now let's actually see how this reaction progressed. So here I went from my acid, and it goes all the way over here to that, which is going to be my conjugate base. And then here I have my NH3. It went over here to NH4, which would be my conjugate acid. Okay, we've got my acid. Acid is bonded, or acid is compared to my conjugate base. And then I've got my base, and it is compared to the conjugate acid. All right, so let's do another one, and then I will have y'all dive on into this, a couple of practice problems on your own. So here I have H2CO3 plus NO3 minus, and it's going to produce what? All right, so let's look at this. So here I've got H2CO3. Well, what is that? Well, that would be carbonic acid. So this would be my acid, which means this would be my base. So this is going to give away a hydrogen here. So we're going to get HNO3 plus, HCO3 minus. Okay, so let's see what happened. So here, our H2CO3 turned into HCO3. So my acid is bonded with the conjugate base there. We're going to connect it there so we can figure out what is the acid and what is the conjugate base. My base, we're going to connect to my conjugate acid. And that's going to show us just kind of how that reaction progressed as we went through this overall reaction. Now, again, a couple times I've said this is bonded to this. No, there's not actually a bond that forms or anything like that. What I'm trying to say is that we connect those two things together, and we're trying to see what is the acid, because it's going to be represented by that conjugate base after that reaction has completed. What is the base? Because it's going to be represented by the conjugate acid when it's completed. So during this neutralization reaction, we're going to see that conjugate base and that conjugate acid as a result, as a part of those products. Okay? All right. So I want y'all to go ahead and give this next one a try. All right. So go ahead and give this next one a try. So pause your video, work this problem, and then we'll go over it. Okay, so here is what you should have ended up with. So here, H2CO3 is carbonic acid again. That is an acid. We've got our water here. Now remember, water is what we call amphoteric. And amphoteric means it could act as either an acid or a base. And so how do I know what it's going to act as? Well, if it's working with an acid, then it's going to act as a base. If it's working with a base, it's going to act as an acid. And so just kind of keep that in mind when you're looking at this. Water can be a proton donor or a proton acceptor. Now, in this case, it was a proton acceptor, and so water was the base, and it turned into our H3O plus there, which would make that H3O plus a conjugate acid. My carbonic acid, it's going to donate its proton over there to that water, and as a result, its conjugate base will be HCO3 minus. Okay? All right, now this next one, I'm actually going to work with you. Normally, I kind of let y'all do a couple of these practice problems on your own, but this next one I want to work with you because HCO3 is also amphoteric. So since HCO3 is also amphoteric, because water is also amphoteric, how do I know what's going on? Well, since they didn't tell us what's going to act as the acid or the base, either one could be written. So the HCO3 could act as the acid, or it could act as the base. And so let's actually see what that looks like. So if the HCO3 is acting as an acid, acting as a proton donor, then this would give away a hydrogen, and we would get H3O plus CO3 minus 2, right? So that is something that could happen. Or I could have the HCO3 minus acting as a base, so plus H2O, which means my water would act as an acid, so it's going to donate that hydrogen. So then if that happens, then we would produce H2CO3 and OH minus. Okay, so either way, these are both acceptable answers. We're just seeing that different result based off of what happened. One is acting as an acid and one is acting as a base, right? So I'm going to actually leave this last one, this NH3 plus H2O, for y'all to do on your own. But if you want to check back on your key, by all means, please do so, because you can find the answer here on your the notes key. All right. All right. Now, in the past, we did have acid-base definitions for by Arrhenius, and Arrhenius basically was just saying that acids are substances that contain hydrogen that can dissolve in water and produce hydrogen ions. Bases are substances that contain hydroxide and dissolve in water and produce hydroxide ions. But we know that that's not necessarily always the case. For example, ammonia, which is NH3, there's no hydroxide in ammonia, and so as a result, we can't still use that definition, all right? And so we have kind of moved on past that, all right? Now, if we do have a neutral solution, we know that neutral solutions are neither acidic nor basic, and what's going to happen is they're going to contain an equal amount of hydrogen ions and hydroxide ions, all right? Okay, so now moving on. Neutralization reactions. So we know that acids and bases have contrasting chemical properties. So we say that one is acidic versus basic. We say that, like if we're talking about properties, one is sour and one is bitter. Like they do different things, right? And so when we mix an acid and a base together, they're actually going to neutralize, which means to cancel out each other. Okay, and sometimes that can be a very, very reactive thing, and other times we'll just see something like a little bit of bubbles. Now, when we mix those together, when we neutralize them, we are going to cancel out those extreme effects, right? So it's not going to act like a strong acid or a strong base anymore because we're canceling out those things. When you add just enough base to an acid, we say that that acid is neutralized, or vice versa, right? I technically could add just enough acid to neutralize a base. And when my moles of acid equal my moles of base, each reactant is neutralized, and therefore we're going to start creating a salt, right? So ionic compounds and water, because as a part of our neutralization reactions, we should be producing water. Why? We've got our hydrogen, we've got our hydroxide, they're going to bond with one another and they're going to form H2O. All right, so water. And then everything left over is going to be your ionic compound, that salt. All right, so let's predict the products of the following neutralization reactions. Again, how do I know this is neutralization? Well, I know H2SO4 is an acid, and I know KOH is a base. So since I've got an acid and a base, it's a neutralization reaction. So looking at this, what's actually happening? Well, we're going to have that water created, and then we're going to have a salt created. So what does that look like? So I have K2SO4. Okay, how did I know it was K2SO4? Well, my potassium is going to bond with my sulfate there. Potassium has a +1 charge, sulfate has a -2 charge. So we had to cancel those charges out. So we're going to need 2 potassium, 2 positive charges to cancel out that -2 charge. Plus, well, what am I left over with? H2O, so HOH, right? And then I would need to go back in and balance. So that's going to require me putting a 2 right there and a 2 right there, and then we would have our balanced equation. Okay? So I want y'all to go ahead and predict the products for the next 2 reactions. So predict the products for the strontium hydroxide plus HBr, predict the products for the HNO3 plus RBOH, and then we'll see what happens. All right? So pause your video. Okay, so this is what you should have gotten. So for that first reaction I had y'all work, so the strontium hydroxide there plus the hydrobromic acid, we're going to produce strontium bromide plus water, and we're going to need to go back in and balance it. So you would need 2 hydrobromic, and you would need 2 H2O to make that balanced. All right, and then if you did the HNO3 plus the RBOH, we're going to produce RbNO3, again, +1, -1 charges, they cancel out, plus H2O. It is already balanced, so we did not need any coefficients. All right. So moving on. So now that y'all kind of have a general idea of how to predict the products for an acid-base reaction, so for this neutralization reaction that's occurring, when a strong acid reacts with a strong base, the net ionic reaction is, every single time, it is H plus OH should produce H2O. Now, why do we not have those ions produced for that H2O? Well, 1, it's a liquid, right? Water does not dissolve in water. But 2, it's a covalent compound, so there's no ionic bonds that are forming. As a result, there can't be ions that are produced. Okay, now, that's if we react a strong acid with a strong base. So what happens if we don't have a strong something in one of them? So like if I've got a strong acid and a weak base, or a weak acid and a strong base. So what's going to happen is the reaction is going to go to completion, and the weak substance is going to ionize completely. So why do I say this? Well, because if you remember, our strong acids and strong bases are going to completely dissociate, right? So they're going to completely ionize. However, weak acids don't normally do that. And so as a result, when we take something like our acetic acid here and we put it into that base, we're going to start off as acetic acid. It is dissolved in water, but it's not ionized in water. It only partially ionizes in water. And so it's going to then react with that base, and it will then completely ionize. So it's actually going to completely break down, and you're going to be left with a net ionic equation, something similar to what you see right here. Okay, so just kind of keep in mind that if we've got a strong acid and a weak base, or a weak acid and a strong base, then the weak substance is always going to ionize completely. Okay? All right. So, next thing with acids and bases is a titration. So titrations are also called volumetric analysis. And basically what it is it's a process where we're going to add a solution of known concentration to another solution, And we're doing that so that we are going to be able to analyze what's going on with that other solution. All right. Now, we've got two parts to our titration. We've got our titrant, which is going to be the solution of known concentration. And then we've also got our titrand, or analyte, which is going to be the solution that we're trying to predict what it actually is, or the concentration that it actually is. Okay? Now, when we're doing a titration, we are going for something called the equivalence point. Now, essentially what that is that's the point where if I have reached it, the substance is going to be completely reacted. So we've hit a point to where we're not adding so much more of the titrant that we're actually overpowering the titrand, but we've added enough to where everything is completely neutralized. Okay, so we're kind of at this equivalence point, this place where they are both equal. All right. Now, we also are going to add an indicator when we're talking about a titration. Why? Because a lot of times we're going to use a titration with acid-base reactions. So you need to be able to recognize when the substance is still acidic. And a lot of times we're going to add an indicator that for the purposes of acid-base reactions is going to be pink. And so essentially you're going to be adding in that titrant until you actually hit the point where it's very, very slightly pink. And then that would be where you know that you've reached your equivalence point. Okay. The very last thing is going to be the end point. Okay. That end point is the place where the indicator has just changed color. Okay. So it has just changed color. And so that's where we start to see that very slight pink occur with an acid-base reaction. Okay. All right. So what volume of a 0.100 molar hydrochloric acid solution is needed to neutralize 25 milliliters of 0.350 molar sodium hydroxide? So first thing that you're going to need to do is actually write your balanced equation. So we know we have hydrochloric acid, so HCl. We know we've also got sodium hydroxide, NaOH. And I need to recognize if these are strong acids and strong bases. So hydrochloric acid, sono-clo-clo-bricyl. So it is that cl in bricyl. So HCl is a strong acid. Then I've got sodium hydroxide here. Remember, with your strong bases, it's going to be everything from group 1 with the exception of hydrogen, so the first one. And then everything in group 2 with the exception of the first two, so beryllium and magnesium. So this is going to be something from group 1 that is not hydrogen, so that is also a strong base. So I've got a strong acid and a strong base, so they're going to cause the reaction that will always produce water and salt. Okay, and in this case, it was table salt, NaCl. So the water, again, came from H plus OH, and the NaCl came from Na and Cl. I would need to double check to make sure it's balanced. In this case, it is already balanced for me because everything's got a positive or negative 1 charge, and so we do have our balanced chemical equation. Now, the question asks, what volume is needed to neutralize 25 milliliters of a 0.35 molar sodium hydroxide? Well, to neutralize it, that means our hydrogen concentration equals our hydroxide concentration. So we're going to want to neutralize to make sure that our hydrogen and our hydroxide concentrations are equal to one another. So how do I do this? Well, I'm going to start with the volume I am given. So I have 25 milliliters. And they're wanting to know the volume of the other substance. Well, to do that, I'm going to actually have to work my way all the way through stoichiometry until I end up with the volume that I need. So 25 milliliters of NaOH. And I ask myself, is milliliters of NaOH what I'm looking for? No, it's not. So I drop it low. And I'm actually going to convert this into liters. Now, why would I do that? Well, I would do that because remember, molarity is moles per liter. And why do I need to use molarity? Well, molarity is a good way to get from concentration, so a substance of one substance to another substance by getting moles. And we need to get to moles because moles is the only way we can go from one substance to another. We do that using our mole-to-mole ratio. So milliliters into liters. So I know that there are 1,000 milliliters in 1 liter of NaOH. And then we're going to go from liters of NaOH into moles of NaOH using our molarity. So I know that I had a molarity of 0.350 moles per 1 liter. All right, I'm going to zoom in a little bit for you. But moles of NaOH is not what I'm looking for. I'm trying to get into hydrochloric acid, specifically the volume. So I'm going to go from moles of NaOH into moles of HCl. How do I do that? Well, I do that using my mole-to-mole ratio. So looking right here, I have 1 HCl for every 1 NaOH. So 1 HCl for every 1 NaOH. So it's a 1-to-1 ratio. Well, now I'm in moles of HCl, so then I can go from moles of HCl into liters of HCl using my concentration right here. So I have 0.100 moles for every 1 liter. And then the last thing, if they're looking for volume, technically we would be in volume if we stopped here, but we should probably keep them in the same unit. So then we would go from liters of HCl into milliliters of HCl, and it's 1 for every 1,000. Okay, so plug that into our calculator, and what we would end up with is we have 87.5 milliliters of HCl. And then that would be my answer. All right. So that's kind of a basic titration problem. Very, very simple in terms of how we do it. So let's take a look at a little bit more in-depth problem here. So it says a student carries out an experiment to determine the exact concentration of a sodium hydroxide solution. To do this, the student weighs out 1.3009 gram sample of potassium hydrogen thiolate. Okay, so that is KHC8H4O4, but we oftentimes will abbreviate that as KHP. So I have my KHP, which has a molar mass of 204.22 grams per mole, and that has 1 acetic hydrogen. Now this is actually important. This is what we call monoprotic. Monoprotic. And what that means is it's got 1 hydrogen to actually give away as a part of this reaction. Okay. Now the student dissolves the KHP in distilled water, adds phenolphthalein as an indicator, and then titrates the resulting solution with the sodium hydroxide solution to the phenolphthalein endpoint. The difference between the final and the initial burette reading indicates that 41.20 milliliters of sodium hydroxide solution is required to react exactly with 1.3009 KHP. So then they want us to calculate the concentration of the sodium hydroxide. So how do I do this? Well, first off, I know that I'm trying to cancel out this much, right? So we're going to actually go from grams of KHP, and we're going to actually solve for hydrogen. Well, why would I solve for hydrogen? Well, I'm going to solve for hydrogen because remember that if I am completely canceling something out, so my H plus equals my OH minus. So my hydrogen concentration equals my hydroxide concentration, which means I'm actually going to, if I can solve for my hydrogen concentration, then I should be able to also know what my hydroxide concentration is, right? Because they're going to equal each other. Okay, so I'm going to convert from grams of KHP into moles of H+. So how do I do that? So I have 1.3009 grams of KHP. And I was told that to convert from grams into moles, I can use my molar mass, which is 204.22 grams for every 1 mole of KHP. Okay, so now I'm in moles. So then how do I get into my hydrogen concentration? Well, I have moles of KHP. And remember where they told us that it was monoprotic? So it's got 1 hydrogen to react. So for every 1 mole of KHP, we've got 1 hydrogen ion that we can use. Okay, so I'm going to plug that into my calculator, and I'm going to get 0.006371 moles of hydrogen ions. Okay, now again, remember, moles of hydrogen ions equal moles of hydroxide ions. So now I know that my hydroxide ions also have to be 0.006370 moles. So 0.006370 moles of hydroxide, OH minus. Okay, so now I know that, but that's not what it's asking. It's asking for my concentration, right? So I need to convert from my concentration, the concentration of the sodium hydroxide. So I need to convert from my concentration of hydroxide ions into sodium hydroxide and then use that to convert into my molarity. So I have 0.006370 moles of OH. We're going to go from moles of OH minus into moles of sodium hydroxide. And we know that we have 1 mole of sodium hydroxide for every 1 mole of OH. How do I know that? Well, sodium hydroxide is NaOH. It is a 1-to-1 ratio there. Okay, so now I'm going to solve for my moles of sodium hydroxide, which is again 0.006371 moles of hydrogen ions. So now what do I do? Well, remember molarity is moles per liter. But this is my number of moles in the volume that I have. So I know that I needed 41.20 milliliters of the sodium hydroxide solution. So I have this many moles in that volume. So I'm going to take this, because it's moles per liter. It's moles of solute over liters of solution. So I have per liter, which would be 0.04120 liters, not milliliters, liters. Okay, it was that 0.04120 because I converted it into liters. So liters of H. Okay. So now I've got moles over liters. So I can plug that in and I will find that I have 0.1546 as my concentration of NaOH. Okay, and so yeah, that was a little bit more complicated in how we solved it, but ultimately it's something that y'all have done before. Just remember, the biggest thing to remember is that your moles of hydrogen ions equal your moles of hydroxide ions. So they're going to be an equal ratio that we have there. Okay, that's the way we end up with a neutralization. Your amount of hydrogen equals your amount of hydroxide. Okay, all right, y'all, that is it for our acid-base reaction notes. As always, reach out if you've got any questions. But otherwise, y'all have a great rest of the day. Bye, y'all.